Welcome back everyone to our continued discussion on comparison plots, specifically the joint plot Seaborn call as well as the pair plot Seaborn call. Here in part 2 we're actually going to head over to the notebook, explore how to call the plots within Seaborn, and then the various adjustments with arguments and parameters you can call on these plot types. Let's head over to a Jupyter Notebook and get started. Alright, here I am at the Jupyter Notebook. I've gone ahead and done the various imports, NumPy, Pandas, Matplotlib.pyplot, and Seaborn, and we're going to be working with the students performance.csv file that we've already are familiar with, and here's the head of that data frame. And essentially, for the joint plot that we're first going to explore, it's really similar to a scatter plot. It's just additional information on top of that scatter plot. So what we need here are two continuous features, one for the x-axis and then one for the y-axis. And we have these continuous features in math score, reading score, and writing score, essentially allowing us to answer the question, is there a relationship between the math score and the reading score, or math score and the writing score? If someone scores really well on math, are they also really likely to score well on reading and writing? So the way we can do this is by saying sns.jointPlot, and the very basic calls look exactly the same as a normal scatter plot. You say the source of your data, you ask what you want on the x-axis, so we'll say math score, and let's compare it to the reading score along the y-axis. So by default, you run this, and essentially what you see here is the scatter plot, math score versus reading score, with the additional information of the distribution of each of those features. So here on top, this relates to the math score. So this is the histogram here on top of the math score, the x-axis. And then over here on the right-hand side is the histogram for the reading score. So you can see the distribution within the reading score. And then essentially all these points are where they match up. Now one of the main parameters here that you can adjust is what you actually want to see inside that is not a scatter plot, for instance. And the call for this is kind. So if you scroll down here or see the doc signature, you'll notice by default kind is a scatter plot. But there's a couple of other strings you can call. Some of the more common ones are hex, which is the hexagonal plot instead. And what this does is going to draw a bunch of, essentially a grid of hexagons on top of this scatter plot, count how many points fall within each hexagon, and then just darken the hexagons based on how many points fall within each one. And this is nice because the way the plot is right now, actually I'm not entirely sure how many points are stacked on top of each other in this particular scatter plot. But with hexagon, it shows me that we clearly have a lot of points stacked here in these darker areas. And again, if you wanted to, you could just keep the kind as scatter. And then if you wanted to, you could adjust the alpha parameter instead and say alpha maybe is equal to something like 0.2. And you can then begin to try to explore how many points are stacked on top of each other that way. So you have two options here. One is going with the one is going with the hexagonal route, where you see these hexagons and then you darken the hexagons, or you can go this alpha route in order to try to give more information for where points are stacked on top of each other. There's also the histogram style, which essentially is going to be a bunch of square blocks. So if you say HIST as your kind and run that, instead of hexagons, it's just doing it as kind of straight blocks. But what's nice about this is it lines up with the bins of the histograms themselves, which I really like. So you can see here that we have this bar for this histogram, and we scroll down, it eventually lines up with all these bars on the right side of the histogram. Keep in mind though, you do get to see kind of this pixelated blocky image, which may be unclear to people who have not seen this plot type before. Most people can instantly understand what a scatter plot is, but if you eventually jump straight to kind of this histogram 2D distribution, it may be unclear what they're actually looking at. And the other kind you can do here is come back up here and say, instead of hist, show KDE. And essentially that replaces the histograms with KDEs and shows you this two-dimensional KDE where they cross over. And this one's unshaded by default, but if you can say shade is equal to true here, run that, and it will shade in that histogram. And of course, you can always edit the palette to any color mapping you want within Matplotlib. So we always have that palette option as well. And what's interesting is then we also have the option for hues. So let's go back to the defaults of the scatter plot. So here we can see the scatter plot, but what we can also do is say hue is equal to gender in order to try to reveal more information. And when you say hue, what's going to happen is instead of trying to stack histograms on top of each other, which is really hard to read, it creates two separate KDEs per hue per continuous feature. And then it will also show you the points themselves. And I think this is the best way to show the actual information, because this is where you really get to see the strengths of the joint plot versus just calling a scatter plot. It allows you to directly compare not just the continuous features, but also the distributions within each category for different categories themselves, like gender, female versus male, for math score, as well as reading score. So you can see where the differences are between each. Okay, so again, that is the hue parameter, and as always, you can edit that palette coloring. So let's go ahead and move on to the idea of the pair plot. And the pair plot, we always want to be careful with it because it is quite CPU intensive. And let's just call it so we can understand why it's so intensive. I'm going to say SNS.pairPlot, and this one's the simplest to call because you essentially just say what your data is. So notice right off the bat, you just say data, and if you expand on this, then we see the rest of the parameters. But we say df, or we can say data is equal to df, or you just pass in df. Run that, and you'll notice it creates this pair grid, and along the central axes, or along the diagonal, we have the histograms for each of those continuous features. So I didn't have to do any filtering, and if we look back at the data frame, what it did is it grabbed all the numerical columns, which is math score, reading score, and writing score, and then automatically shows you the histogram distribution for each, as well as the relationship between each of the combinations. So reading score versus math score, reading score versus writing score, and writing score versus math score as well. And because of this, you essentially get duplicates along the diagonal. So you notice here, bottom middle, I have reading score versus writing score, which is the exact same plot being shown here in middle right, writing score versus reading score here. So it's essentially the same along the diagonal, which is why if you want, you can turn off the upper diagonal. So the other thing to note here is I can add in a hue. So I can again separate out all this information based off something like gender. And as I noted before, when you're separating out different categories, it's really hard to read in a stacked histogram or histogram stacked on top of each other, which is why when you add in that hue, it automatically fixes the diagonal to be a KDE for you, which is much easier to read when you're comparing two separate categories. However, it should be noted, if you really want to, you can always specify that you do want the diagonal to remain a histogram. And you can do this with diag_kind is equal to hist. Run that, and it will keep the histogram diagonal. Although in my opinion, it's a little tougher to read these histograms kind of stacked on top of each other versus the KDEs themselves. And the way this works is you can kind of see the difference over the unoverlapping shaded area. So again, harder to read this, which is why by default it shows you the KDEs, which is an easier way of comparing the distributions. And as I mentioned, you'll notice that this one took a little bit more time to run than these joint plots, and that's because it's dealing with essentially the entire data frame. So always be careful when calling the pair plot on a super large data frame. Other things to note here is we can say corner is equal to true to essentially say I only want to show one corner and not these duplicate plots. And so when you run that, it gets rid of the duplicates and just shows you one corner. And this is essentially showing all the same information that we saw before. Okay, so that's it for the pair plot, and this is pretty much as far as we'll take it throughout the course, because after a certain point, you may just want to filter down and explore features yourself. Because the more features you have, the larger the pair plot gets, and after a certain point, if you have a 10 by 10 grid of all these feature combinations, it becomes really hard to kind of narrow down what you're actually looking at. So in general, we select a sub-filter of the columns we're interested in. In this case, we only had 3 numerical columns, so the pair plot wasn't a big deal. But if you have, for instance, 20 numerical columns, filter out by the ones you're most interested in, maybe the ones that are most correlated with each other, and then go ahead and call a pair plot on that. And then if you see an interesting relationship, such as, let's say, math score versus writing score, or math score versus reading score, so for example, let's say we were really interested in math score versus reading score, then you would come back after running the pair plot and explore that deeper with a joint plot. So again, the way I like to do this, you call a pair plot after filtering out the data frame columns, and then based off what you're interested in from the pair plot, dive in deeper with the joint plot, see it larger, and then explore the distributions there. Okay, that's it for this lecture. I'll see you at the next one.